Upgradability patterns for smart contracts are becoming more and more prevalent, and of course along with that comes a lot more and more different types of vulnerabilities related to smart contract upgrades as well. So in this video we're going to overview 5 different upgradability patterns and have a look at the potential mishaps and vulnerabilities that can occur with each one, and as well as discuss the upsides of each different upgradability pattern. But real quick, of course, before we dive in, my name is Owen, and over a year and a half ago, I founded Guardian Audits, and ever since then, we've uncovered dozens and dozens and dozens of critical and high vulnerabilities, and have personally spent easily over 1,000 hours auditing smart contracts along the way, and my goal is to distill down everything I've learned from the entire process and give it to you in these videos so that you can ultimately become a much better smart contract developer, smart contract auditor, whatever it is that you're looking to be, in a fraction of the time while avoiding all of the mistakes and things that I had to go through along the way. All right, without further ado, let's get into upgradable smart contracts. All right, like I said, today we're going to examine 5 different standards of smart contract upgradability, and these are eternal storage, transparent proxies, universally upgradable proxies or UUPS, beacon proxies, and of course, last but certainly not least is the diamond standard. All right, great. So let's just dive in and start talking about eternal storage. So this is the only upgradability method on this list that doesn't actually use delegate call or any sort of proxy-like implementation. Actually, the idea of the eternal storage pattern is to have a contract that is dedicated to just holding all of the important data of the smart contract application, and then to have the logic contracts implemented around that can basically call functions on the data contract and actually cause manipulations within that contract storage. And so this way we have effectively separated the logic contracts from the contract that houses all of the data. And so if you need to upgrade the logic of the protocol, you can change out one of the logic contracts over here and just deploy a new contract that has the same permissions to talk to this data contract. And so if we were to basically just sort of map out what's going on here, is we have one contract over here, which is responsible for housing all of the data. We'll put a D right there. And then we have, one or more, potentially several contracts that are used for the logic. So I'll put an L right there. And so we could have several of these. If I actually copied everything, we could have several of these logic contracts. I'll just delete this. Several of these logic contracts that all have the permissions to basically talk to this data contract and execute functions on the data contract that will actually change the storage within the data contract, and then also they'll read from the state of the data contract to get the state of the system. And so these logic contracts don't actually store any important state. They're all deriving the state of the system and writing the state of the system to this data contract. And so if I need an upgrade on a very specific part of the protocol, I can take this logic contract out and I can put in a new one that is just, talking to the data system in the new upgraded way. And so obviously one potential flaw here is if a user has to interact with this logic contract and then we pull this little switcheroo where we take the existing logic contract out and we put a new one in, and so it will have, it will be at a different address, of course. So now if we started using this one and saying like, this is now the logic contract that actually is, the valid, most updated logic contract, and this could be at address OXA, and then of course this old one was at OXB. Now if users are, they have been interacting with address OXB, now you have to tell everybody to go and look, now OXA, this is the real contract that is now being used. And so you'd have to tell users to basically migrate to that implementation. But of course you can solve all of this if you just separate the user's transaction if I basically come and say, if I come and I take this and I say, nope, we don't have the users interacting with the logic contracts directly, but we have instead, we come and we take and we implement, like a router or something like this on top, which basically says that, okay, this is the router, this is the user interface for the system, and then the router will go and the router goes and it talks to the logic contracts, and the router knows which is the most up-to-date logic contract. And so if we switch a logic contract out here, the router will automatically go to the correct logic contract, and the user can continue to interact with the router at whatever address the router is at. And so, of course, a fantastic example of this particular upgradability pattern is implemented in the GMX v2 codebase. So we can see here that they have a data store contract here up at the top, and this is that data contract here. If we go right here, this data contract right here is basically the data store, and we can see we have basically mappings, tons of different mappings for different values. So uint values that are stored in the data store, they map from a bytes 32 object to a uint 256, and we have all different kinds of mappings for Boolean values, string values, more bytes 32 values, and then we implement all of these functions which are permissioned. That's very important, to set all of these different values in this data contract. And so only the contracts with permission to, set a value in here can actually set that value and change the state of the protocol in this data contract. So of course, each of these logic contracts is going to have that controller permission to be able to actually manipulate the data inside of the data store. And then of course, they have an exchange router up front, which the users are interacting with, which will then take and, sort of send them off to, if they need to interact with this logic contract, which implements a logic for increasing a position or, things such as this. And of course, if you're interested in learning more about this pattern, you can check out the GMX Synthetics GMX v2 codebase in the description down below. And so of course, the good things about eternal storage are perhaps its simplicity. You don't have to worry about selector clashing or storage collisions, these things that just come up with the delegate call types of implementations. And of course, you can easily replace contracts in the system by just swapping out, one of these logic contracts. And of course, a common pitfall, common mistake that is, of course, if you don't have, you don't manage access control properly. Of course, if, like one of these functions didn't have a modifier in it and it was just an external function, that would be a critical vulnerability. And then of course, managing access, if there is a logic contract that is found to be malicious and it needs to be upgraded, then we need to make sure that we remove the controller status from that contract. Okay, so that brings us to our first of the delegate call type implementations for upgradability, and this is of course the transparent proxy. And so first, before we dive into the actual implementation of what a transparent proxy is and what it looks like, let's first talk about just delegate call. So delegate call comes into play when, let's say, we have two different contracts. We have a contract here. This will be our contract A. Actually, let's call this our proxy. And then what we can do is we'll have another contract and let's call it an implementation. All right, so there's our poorly labeled implementation contract. So how delegate call is going to work is, let's say that we want to have the proxy delegate call to the implementation. So when we delegate call, basically what we're going to do is we are delegating control of this smart contracts environment to this implementation contract. So we're going to allow this implementation contract's logic within, the functions inside of the implementation contract to have an effect on the storage in the proxy contract over here. And so basically it's like if I was a user and I come from my EOA over here, and then I call into this proxy contract and I say, I'm going to call XYZ function on this proxy contract. what we're going to say is we're going to maintain all of the state of this current transaction that I'm making, and we're going to say, okay, basically, what would this implementation contract do if it was almost like I came and I just called the implementation directly? So what we're going to do is we have this transaction that gets started, and there is a message.sender associated with that. That is my EOA. There is an address this of the current execution environment, and that is the proxy contract. There is, of course, a message.value that would have been provided, as well as a few other things. But basically, we're going to take all of this data within the transaction, so the message sender, address this, message.value, among other things, and we're going to preserve it when we delegate call to the implementation. So it will be as if we called the implementation and it has the exact same thing. So message.sender, when we're within this delegate call execution on the implementation contract, message.sender is going to be this EOA here, and then address this is going to be the actual proxy address, and message.value will be, whatever message.value the EOA sent, and essentially any logic that happens that would store stuff in storage or emit events or anything like that, that is going to happen in this proxy contract. So if I have something in the implementation contract that says store something at storage slot 1, we're going to come and inside of the proxy contract during this execution, we're going to store stuff at storage slot 1. And of course, this is going to lead to a number of different potential hiccups and vulnerabilities that we're going to see with these delegate call type upgradable patterns. So the idea behind the transparent proxy is that on this proxy contract, there is an implementation stored. So we have a storage variable that is the implementation stored somewhere within this proxy contract. And then that storage variable stores an address, and the address is the exact address of the implementation contract that we ought to delegate call to whenever we receive any kind of message from an EOA. And so basically this implementation address here is saying, what is the contents of this contract essentially? What is the logic of this contract? And so by changing the implementation, I'm able to change the actual implementation of the code that is, conceivably being executed on the proxy when you call it. All right, so let's have a look at the implementation for a transparent upgradable proxy. So first of all, we'll note that this inherits from an ERC1967 proxy. And so I'm going to click into this so we can see what this looks like before we move on. So this inherits from a normal, just base proxy. So let's have a look at what a normal base proxy is. And so at its core, this base proxy is just a contract that has this underscore delegate function. And whenever you hit its fallback function, you will just delegate to the implementation, which is received from the invocation of this implementation function. So in this delegate function, which is up here, we can see all we're doing is we're just literally getting all of the call data for the transaction and just copying it entirely into memory. And then what we're doing is we're immediately just delegate calling, forwarding all of the gas to the implementation contract, which was received from the invocation of this implementation function right here. And then so we're basically going to get the call data size. We're going to have, basically just provide from 0 to, however bit large the call data is, just have all of that call data available in the delegate call. And then here we're going to copy the return data into memory so that we can then revert in the case of a revert with all of that return data, or return that actual return data. And so really at a high level, the only thing this function is doing is just delegate calling to the implementation. So we take whatever call data the user provided in their transaction, basically just throw it, give it to the implementation, and then we will, handle the return data, handle success or failure. So then the next interesting thing we need to ask ourselves is, where do we get the implementation, right? So the implementation function is not actually implemented in this base proxy class. So if we go back up a level to the ERC1967 proxy, we can see that the implementation is using this erc1967utils.getImplementation function. Now, before we look at this function, let's see like what is erc1967. So if we click and we go to the erc1967 EIP page, we can see that this ERC is specifically just focused on having a consistent location for proxies to store the address of the logic contract, the implementation contract, right? So if we scroll down here, we can see that that particular address, that particular storage slot that this address should be stored at is this right here. It is the bytes 32 value of a hash of this string here, and then with a 1 subtracted from it to make it even more exotic. And so the result of that is, of course, this big 32 byte object here, and then this is the storage slot where the address for the implementation is stored. So when we go into this erc1967utils function for getting the implementation, we see we're basically just accessing an address slot. So we're just accessing the storage slot that's here, and then we are basically getting that value as an address. And of course, the implementation slot is our hash here. So we can see 3608, 3608, and it ends with BBC, and we've got BBC right there. Okay, fantastic. So at this point, we still haven't even actually talked about specifically a transparent upgradable proxy. This is just an ERC1967 compliant proxy. And so this is the base proxy that the transparent upgradable proxy is building on top of. So we can see it inherits from the ERC1967 proxy, and then it implements a fallback function. So it overrides the fallback function, and then we can see that it also has an internal function here. So what is going on? What makes this implementation specifically a transparent proxy? So really the key features of a transparent proxy is that this admin here is stored in this proxy, and the admin actually is able to control whether or not a upgrade happens from this proxy contract. So what I mean by that is, of course, we can see with these lines here, this is actually all of the logic that holds basically the logic to go from one implementation contract right here to upgrade and have the proxy point to a different implementation contract. So basically all of the logic to say, hey, this old implementation was bad, now let's go to a new one and have a completely different implementation contract over here, all of that logic lives right here. So let's have a look at it. So if the message.sender happens to be the admin calling this proxy, and the message.signature, the first 4 bytes of the call data, is for this upgrade to and call selector. So essentially if they wanted to call the upgrade to and call function and they are the admin, then we're going to call this internal private function dispatch upgrade to and call. So what this is going to do is it's going to take the message.data, we're going to slice off those first 4 bytes of the selector. We're going to decode 2 things: the address of the new implementation, so that's expected to be called first in the call data, and then some just arbitrary bytes that we want to be invoked on the new implementation when we call it. And so then we're going to upgrade to and call, and we'll see what this does. We're going to set the implementation, so this is where the upgrade is actually happening. Now we're writing to that storage slot, so we can go in here and we can see we're writing to the implementation slot, we're setting the value to the new implementation. And this is exactly where the upgrade is happening. And then after that, of course, if the length of the data is greater than 0, then we're going to, give like an initialization call or whatever you would like to actually call on the new implementation. It can be any of this arbitrary data here. And then if it's not, we have a safety check to make sure that they didn't accidentally send some message.value along with this upgrade. Okay, so what are the good things about this transparent upgradable proxy? Well, first of all, it's probably the easiest to understand of all of these delegate call type proxies. And of course, it's relatively cheap to just deploy a new transparent upgradable proxy, since it doesn't have to have all of this logic data or anything like that. You can just deploy a new proxy that points to whatever implementation you would like it to for the logic. But of course, what are some downsides of the transparent upgradable proxy? Well, of course, first of all, the admin can't actually interact with the actual implementation because, of course, if the message.sender equals the admin, then we're going to either be able to upgrade or it's just going to revert. And so we're not ever going to be able to enter this else case, which would be for everybody else, in which case we go to the fallback of the ERC1967 proxy, and we would basically do the actual delegating to the implementation. So an admin cannot actually interact with the system because of that. And so on top of that, to basically sort of address that, this admin sort of comes with its own contract. So when they first deploy a new transparent proxy, a new proxy admin is deployed, and that's set to the admin, which is immutable. And so here's the proxy admin contract, just a really simple contract, but it does add complexity to just have another contract that's associated with the system. So some might say unideal. But another thing to potentially have to worry about with all of these delegate call upgrade implementations is, of course, function selector clashing and storage collisions. So what are both of these things? Well, if I am delegate calling to an implementation here, and then let's say the implementation said to write to this implementation slot, then this implementation would actually end up writing to the implementation, right? And changing the contract that it actually delegate calls to. And so this can often get quite complex if you have a former implementation contract that had A, B, C, full 32-byte storage variables. And so then each of these storage variables would be stored in the proxy. And then if I wanted to upgrade to a contract that had variables, let's say you had A, B, D, C. Well, now what's going to happen is, since Solidity basically says, okay, what's the order of the storage variables you've declared? That's the order of, the first one's going to go to slot 0, the second one is going to go to slot 20, and so on and so forth. Then now when we have A, B, C in this proxy contract, now what's going to happen is when we upgrade to this one and this one starts writing stuff, we're going to write A to A, B to B. Now D is going to overwrite C, and then now C is basically going to have a new storage slot. So that is one way that storage collision can occur when we're using this sort of messy delegate call behavior. So then what is function selector clashing? Well, that would essentially be if I wanted to call the function with, let's say it had the same selector as add uint256 A, uint256 B, and of course it would return uint256. If I wanted to call this function, or a function that had a similar selector, so we can get a selector for this add function, we can go cast sig, and we can put in our function interface there, and we can get this function selector. So if I just so happened to have a function on the implementation contract that I wanted to call that matched this function selector, if we had our OX7 ... if we had that function selector in this implementation contract, then if I wanted to call it and there was this add function in the transparent proxy here, then when I call the proxy, we're actually just going to call the add function that is directly on the transparent upgradable proxy, instead of falling back and going in here and ultimately calling the implementation contract. And so normally if these functions were in the same Solidity contract, then Solidity would detect the function selector collision and it would change one of the function selectors so that there is no collision. But since we're going across two contracts here, it is very possible for a function selector to collide with something like add or some other function selector. And then in that case, the one that is in the contract being called directly would have a higher priority. Okay, fantastic. So that leads us to our third implementation of upgrade strategies, which is the universally upgradable pattern or UUPS. And essentially, the difference between UUPS and transparent proxies is just that the upgrade and admin logic for the proxy and implementation system lives within the implementation rather than living within the proxy contract. Okay, so let's have a look at the UUPS implementation, and we can see a few functions here. It's a little bit more robust than the transparent proxy implementation, and we will see this upgrade to and call UUPS function, which is called within the upgrade to and call public function. And so this is not the proxy contract, this is the implementation contract. So this is an abstract contract that your implementation contract should inherit from. And then this way, even if you were just using a basic bare bones proxy contract with no actual implementation, then you would still have all of the logic that you need to basically perform the upgrade, set the new implementation, and upgrade to a new UUPS implementation. So what are some good things about this UUPS design? Well, so first of all, obviously now in the proxy contract, we don't have to be storing an admin or anything like this or have any additional logic for upgrades to happen. And so as a byproduct of that, of course, now the admin can actually use this system. There's no address that has to be basically reserved for doing upgrades. And of course, now when we are falling back, we don't have to specifically check if the message.sender is the admin every single time. So of course, that's going to give you some gas savings right there. But of course, what are some drawbacks to the system? I think probably the number one foot gun of the system is that the authorize upgrade function has to be, you have to manually override it and implement it in the contract that inherits from UUPS upgradable, and you have to make sure that it correctly implements that access control to make sure that only the admin can authorize an upgrade of the system. Otherwise, if you forget to do that, you do that wrong, then you end up having basically a contract that can just be upgraded to an arbitrary implementation, which basically leaves you with pretty much zero security. And of course, another thing is if you end up upgrading to an implementation that just so happens to not have additional upgrade logic, e.g. if it's not UUPS upgradable compliant, then you can't ever upgrade again because there's no longer any logic in the implementation to actually go and set the implementation address in the proxy to a new implementation. So if you're using this with just a bare bones ERC1967 proxy implementation, then basically there's no way to set this ERC1967 implementation slot if you upgrade to something that doesn't have that capability. But of course, there are measures in place to basically try and mitigate that. And so they have a sort of like proxiable UUID function that is basically like a ping to see if this is something that is, presumably compliant with the UUPS standard. So that does reduce the risk of basically ending up stuck in a contract that can no longer be upgraded. But of course, that risk is still there. It doesn't completely mitigate the issue. And then, of course, you have the same issues since we're using delegate call in the system of potential storage collision or function selector clashing. Okay, so that leads us to our fourth pattern for upgradability, which is the beacon proxy. So the beacon proxy is somewhat aptly named as there can basically be a bunch of individual proxies that all basically read from this one beacon, and the beacon basically tells them this is the implementation address that we are all using, all of these proxies, and so all of them will then delegate call to that implementation. So let's have a look at the implementation for a beacon proxy. So we'll first notice that this is actually not ERC1967 compliant because this proxy doesn't store the implementation address at all. In fact, it just stores the beacon as an immutable variable. So this actually isn't stored in storage in any storage slot. It's actually just stored in the bytecode of the contract. And so the only thing that this proxy does is whenever you call it, of course, we'll go into the proxy and we will hit the fallback function. We'll call the underscore implementation function, which if we go back, all that does is it gets the beacon address, which is stored in the bytecode of this contract, and then we're going to call it. We call the beacon, we call the implementation function on the beacon, and then that is the implementation function that will ultimately be delegated to. If we go back here, fallback, we delegate to the implementation that gets returned there, and then that's where our delegate call and all of that happens there. So then let's check out the upgradable beacon. So this is the contract that is our beacon that tells exactly what the address of the implementation is. And so we can see that this is literally just setting a storage slot here for the implementation. So two very, very simple contracts here for the beacon upgradability approach. We can see we literally just have that view function to read what the implementation is. Then we have a only owner function to basically set the implementation storage slot here, which will change the return value of this view function. And that's pretty much it. And so what are the good things about this pattern is, well, first of all, you can just coordinate the upgrade of several proxies at the same exact time by just simply setting this one storage slot in this one contract. So if I had like, a dozen, 100, 1,000 beacon proxies that were all pointing to this beacon address, if I just change that one storage slot in the upgradable beacon, if I just call this upgrade2 function, well, automatically for all of these beacons, we're going to update the implementation address that ends up getting called immediately for all of them at the same time. And then of course, in the actual beacon proxy, yet again, we have removed that sort of inefficient check of checking the admin, if the admin is the message.sender, on every single delegate call. We do get that little boost of optimization over the transparent proxy. But of course, what are the potential downsides? Well, like always, we have, any potential function selector issues with delegate call if more things were implemented in this beacon proxy. But then we also have an increased risk, perhaps, of storage collision. If you had, imagine if you had 1,000 different beacon proxies that were all listening to one upgradable beacon contract, and some of them were from, they had been used with previous older implementations, and maybe they had some extra storage slots that were previously used, but then now you have newer ones that have, they've only been used with newer implementations and they have sort of a different storage layout. So it can get a little bit complex when we're thinking about 1,000 different proxies, which, all of them could have different slight iterations of this is what the storage layout looked out in 1.2 or whatever, and they could have leftover things in storage. Some of them might not have the storage variables that others have. So it just adds a layer to think about when we're actually going through the upgrade process and what that basically like storage migration needs to look like when you go from one implementation contract to another one. And so that brings us to our final fifth approach to smart contract upgradability, which is the diamond standard. And so as we can see here, the implementation for the diamond standard is actually quite a bit more robust than all of the other ones. And so we don't actually have time to go through all of the implementation in this video today. Perhaps there will be a dedicated video for just the diamond standard in the future, but we can just explain really at a high level all the diamond standard is really supposed to do, because at its core it's actually quite simple. Meanwhile, when you actually get to the implementation level, several things are a bit more complex. So really fundamentally, what does the diamond standard aim to do? Well, basically you can have your canonical proxy contract, and in the diamond standard it will just be called a diamond. So we'll put a D here for this is our diamond. And then we have a mapping basically. So if I want to say for function selector OX for a ... just pick your favorite 4 bytes for this particular function selector, what implementation address do I want to use? So it will be a mapping from this 4-byte function selector to this full address here. And this will say basically for this function, I want you to delegate call to this address. And so I can have multiple of these. I can have the function selector oxbc dot dot dot. I can have that basically be, programmed to delegate call to a different contract at the address fa7 dot dot dot. And so this way I can basically engineer essentially unlimited functionality within a single smart contract by just registering these different functions in this diamond proxy contract. And so then essentially what this looks like is like a contract that's literally just like a switch case, which is like you get in call data, you read the message.sig, you say, okay, does the message signature match this? Does it match this? Well, really you would be looking it up in a mapping, and then you would say, okay, so it was, let's say it was this particular message.sig, so the signature for the function we're trying to call. Then what we're going to do is we're going to come over to this specific contract. So we delegate call to this exact contract that was in the corresponding value for that key in the mapping. So this diamond contract is essentially just a registry for saying when users calls this, where are we going to route them to, and where we're going to delegate call the execution for this proxy contract. And so the diamond standard will essentially allow you to easily change the values in this mapping. So if I want to now change OXBC, if I want to change the implementation contract that gets called for that particular function, then all I have to do is change that one single key value pair in this registry mapping. So obviously the good things about this is that I can have sort of small granular control over the upgrades that happen in my system. I can replace literally single functions at a time if that's what I want to do. And also I can manage very, very large, complex logic with many functions potentially in one single diamond contract. And so of course, what are the bad things about the diamond contract? Well, it's extremely controversial because of we just saw the reference implementation. It is quite dense. There's a lot going on here for just you would expect it to just be like a mapping that goes from a bytes for signature to an address, but turns out there's a lot more to it, and a lot of this contains somewhat arguably superfluous optimizations that might not be necessary. And in addition to that, some of the naming conventions could be somewhat confusing, especially when you're coming from these other upgradability patterns. So of course, a diamond is basically the diamond standard's word for a proxy. The diamond standard has this idea of facets, and a facet is essentially just an implementation contract. So of course, a diamond has multiple facets. A proxy can have multiple implementations within the diamond standard. And then there's this idea of a diamond cut. So when you cut, it means you basically change something in the registry. You either add a new key value pair for the function selector to the address, or you change an existing one, or you remove one. That would be called a diamond cut. And then a diamond loop is just a list of delegated functions. So message.sigs that would be delegated on. And so in general, the complexity and the added jargon can just make it a lot harder for new users to onboard to the standard, and in general just enables a lot more things that could potentially go wrong when things are more complex and harder to understand. And of course, you do have to worry about storage collisions especially, and there's a whole system within the diamond standard to specifically address that problem. All right, that is everything. I hope you learned something cool about these 5 different upgradability mechanisms, and I hope you found this video valuable. And last but not least, before we go, of course, if you are working on a DeFi protocol team or you're building a DeFi protocol, then I want to know about your project. In fact, I want to know about it so much that I will do a free first pass review of any security notes, things that you will want to get addressed before a smart contract audit. When you go and submit an application at guardianaudits.com/quote. And of course, if you know somebody who just so happens to be looking for a smart contract audit, then you can send them over to guardianaudits.com/quote. And of course, if you are interested in upgrading your security game and you want to connect with people from around the world and even get the opportunity to team up with others and compete in real audits of real protocols and work with others to craft a real report with your name on it and even get rewarded for your findings, then go ahead and check out lab.guardianaudits.com and submit an application to join our free community of security auditors. Okay, that is it for this time. I cannot wait to see you in the next one.